The world is standing on the edge of a new era. An era not powered by silicon or speed, but by quantum reality itself. Forget everything you know about computers, because what's coming next doesn't just calculate, it creates. Across the globe, researchers are racing toward one goal: to build machines that think, simulate, and evolve beyond limits. And in 2025, that race reached a new level entirely. These aren't just updates, they're revolutions in physics. Let's start with something shocking. Amazon, the company that delivers your packages, has officially entered the quantum battlefield. No longer just a cloud service giant, Amazon Web Services has built its first-ever quantum chip, a superconducting processor called Ocelot. For years, Amazon's quantum platform, Bracket, relied on hardware made by others, IonQ, Rigetti, and Quera. But now, they've taken control of their own destiny. The Ocelot chip sits inside AWS Labs, silently humming in temperatures colder than deep space. It's not about being the biggest or fastest, not yet. It's about one powerful message. Amazon is building hardware. When a tech titan like Amazon starts crafting real quantum chips, it means the world is finally ready for commercial quantum computing. Banks, biotech firms, and laboratories are already on board. Encryption, molecular simulations, data security, all being tested. Ocelot could make quantum computing as accessible as the cloud itself. And that changes everything. But Amazon's not alone. Around the same time, a breakthrough reshaped the quantum landscape. Scientists began using a technique called circuit knitting. It sounds complex, but its genius lies in simplicity. Instead of waiting for giant 1,000-qubit machines, they split one enormous problem into smaller quantum puzzles. Each part runs on a different chip, and classical computers then stitch the results together. This hybrid method just changed the game, because now we don't need massive quantum processors to make progress. We can simulate chemistry, optimize algorithms, and build models, today with the tools we already have. Platforms like Qiskit, CIRQ, and AWS Braket already support it. Real quantum algorithms are now running, not waiting. Meanwhile, Google is quietly rewriting the rules of endurance. Their Willow processor, built with 105 qubits, was pushed through brutal stress tests this year. Quantum chips are notoriously fragile. Even a tiny vibration or heat spike can collapse them. But Willow held strong through thousands of cycles. It maintained coherence, accuracy, and stability under pressure. Why does that matter? Because stability is the secret to real quantum computing. Speed means nothing if your system collapses mid-calculation. Google's breakthrough proves one thing: quantum chips can finally handle real workloads. And that's where things get interesting. Because Google isn't aiming for headlines, they're aiming for history. Willow could soon power physics simulations, climate models, and even AI systems beyond imagination. The quiet stability tests of today could lead to the most powerful scientific instruments ever built. But just as Google and Amazon rise, IBM enters the scene with something even more ambitious. Not a chip, not a single device, but a modular quantum data center, a system called Quantum System 2. It's a complete network of quantum hardware, linked together like the servers inside a massive supercomputer. Inside it, multiple cryogenic refrigerators keep chips ice cold. Quantum processors communicate through ultra-fast control systems. For the first time ever, a company is treating quantum not like an experiment, but like an infrastructure. This is how the Internet of Quantum begins. It's modular, scalable, and ready to grow with each generation. Think of it as the blueprint for the world's first quantum cloud. One day, thousands of quantum chips could be linked, sharing data and solving problems in parallel. And IBM has just built the foundation. But here's where things take a turn, because quantum power brings both progress and peril. It's not the biggest chip ever made, but it's one of the most reliable in history. And reliability is what makes scale possible. Because soon, multiple Heron chips will connect inside IBM's quantum system too, forming the blueprint of a quantum supercomputer. But while IBM fine-tunes its machines, another tech giant is taking a completely different path. Microsoft isn't chasing qubit counts or processor speed. They're chasing something far rarer, stability itself. Their latest creation, the Majorana 1 chip, doesn't use normal superconducting qubits at all. It uses topological qubits, a form of quantum state so exotic that it resists noise by design. Think of it as a quantum knot, information twisted in a way that the universe itself protects it. These topological qubits have been a scientific dream for over a decade. If they work, they could eliminate the need for endless error correction. Instead of thousands of unstable qubits forming a single logical one, Microsoft's approach could make every qubit stable from birth. It's still experimental, still fragile, still in prototype stage. But if Majorana 1 proves successful, it might reshape everything we know about building quantum hardware. Smaller, cooler, and infinitely more stable. That's the future Microsoft is betting on. And quantum innovation isn't stopping there. Across global research labs, scientists are finding ways to use quantum power for more than computing. One experiment shocked the scientific community this year: the creation of a quantum molecular ruler. Instead of using quantum processors for math or encryption, researchers used nuclear spin echoes to measure molecules. They could now map atomic distances and geometry with precision that no classical microscope can match. It's not just computing, it's quantum sensing. For chemists, biologists, and materials scientists, this breakthrough is priceless. It means we can study molecular structures in their natural states without breaking or altering them under observation. Drug discovery, nanotechnology, even DNA research, all could accelerate faster than ever before. But while labs were celebrating, another discovery sent chills through the physics world. D-Wave, the pioneer of quantum annealing, used its system to simulate something terrifying, a process called false vacuum decay. In theory, it's a moment when a stable region of the universe suddenly drops to a lower energy state, a cosmic event that could rewrite the laws of existence. No classical supercomputer could simulate it accurately, but D-Wave's quantum machine did. Now, to be clear, this doesn't mean the universe is collapsing. It means, for the first time, we have tools powerful enough to model the possibility. Quantum computers are no longer just solving equations. They're exploring reality itself. This is the new frontier. Quantum devices aren't limited to technology anymore. They're becoming instruments of cosmic discovery. From particles to planets, everything is connected through math, and quantum computing is finally speaking that universal language. But this is only the beginning. Because the next discoveries don't just expand science, they challenge the entire concept of computing itself. When IBM, Google, and others reveal what comes next, we'll see machines that defy classical limits entirely. The race for quantum dominance is no longer theoretical. It's here, unfolding in labs, data centers, and cold chambers worldwide. And at the heart of it stands one name: IBM. For years, scientists dreamed of breaking the 1,000-qubit barrier. It was the milestone that separated fantasy from true computation. In 2025, IBM finally shattered that line with Condor, a superconducting chip packing a mind-bending 1,121 qubits. This isn't science fiction. Condor is the largest publicly known quantum processor ever built. It's the moment when quantum computing stopped being a dream and became a physical machine. But Condor's power doesn't just come from numbers. It comes from architecture. Each qubit is connected with unprecedented precision, allowing massive calculations without falling into chaos. Noise reduction, coherence control, and modular scaling. Condor is a symphony of engineering perfection. It doesn't yet outperform classical supercomputers on every task, but it's a signal, a promise, that we're almost there. The same way the first transistor computers in the 1950s looked primitive, Condor represents the first true step toward industrial quantum power. IBM's roadmap doesn't stop here. Condor will serve as the foundation for future clusters, linking multiple chips through Quantum System 2. One day, entire data centers could run on superconducting logic. The world's first quantum cloud isn't decades away. It's forming now. But IBM isn't the only player rewriting the rules of computation. Another breakthrough came from an unexpected field: cryptography. Because this year, scientists achieved what many called impossible, certified quantum randomness. Now, randomness might sound trivial, but it's the backbone of security. Every password, every encrypted transaction, every secret key depends on random numbers. The problem? Classical computers can't truly generate them. Their randomness always follows an algorithm, and if you know the algorithm, you can predict the outcome. Quantum randomness, however, is different. It comes from the unpredictable behavior of particles themselves, an uncertainty built into the fabric of existence. In 2025, a 56-qubit quantum processor produced mathematically verified unpredictability, true randomness. That means banks, governments, and even intelligence agencies can now generate encryption keys that no machine can ever guess. It's pure, provable chaos, the kind that protects the future of data. And that changes global cybersecurity forever. Quantum technology has now moved beyond raw power. It's reaching into every layer of society, from finance and defense to science and communication. Every discovery adds another piece to the puzzle. But there was one moment, one headline, that made even the skeptics go silent. It happened when Google finally proved real quantum advantage. For years, that phrase was tossed around loosely. Companies claimed it, but none could truly back it up. Quantum advantage means a quantum computer solves a practical problem faster than any classical machine on Earth. And in 2005, Google did exactly that. Using an algorithm called quantum echoes on its Willow processor, Google achieved a mind-bending milestone, a physics-grade simulation that ran 13,000 times faster than the world's top supercomputers. No tricks, no approximations, just raw performance. This wasn't random circuit testing like before. It was a real-world algorithm solving a real-world problem. Quantum computing had officially crossed the line. This moment changed the entire landscape overnight. For the first time, quantum wasn't a niche experiment. It was a superior technology. Google's test proved what every researcher had hoped for. Classical systems have finally met their match. It doesn't mean classical computers are obsolete, not yet, but it means certain types of problems, those too complex, chaotic, or molecular, now belong to the quantum world. From drug design to fusion modeling, from materials research to financial forecasting, tasks that once took months could soon take minutes. And this is only version 1. So, what happens next? When machines can calculate beyond comprehension, when encryption becomes unbreakable, and when simulation mimics reality itself, what's left for humanity to control? Because the final phase of this revolution isn't about hardware. It's about what happens after quantum computers surpass us. And that's where the real story begins. The age of quantum computing has begun. But what comes next might be far beyond human imagination. Because now, the question isn't can quantum computers work? It's what will they become once they do? Every leap so far, every chip, every qubit, has brought us closer to something both powerful and dangerous. A machine that doesn't just calculate data, but begins to understand patterns of existence itself. Here's the truth. Quantum computing isn't just about speed. It's about how reality behaves at its most fundamental level. Every atom, every decision, every thought, they all follow the laws of quantum probability. So, what happens when our computers finally do too? Experts believe that merging AI with quantum hardware could give birth to a completely new kind of intelligence. Not artificial, not biological. Something in between: synthetic consciousness. AI systems today, like ChatGPT or Gemini, run on classical logic. They process language, learn patterns, and simulate emotion. But they don't truly think. They predict. Quantum systems, however, operate in superposition, where every possibility exists at once. That means a quantum-enhanced AI wouldn't predict outcomes. It would explore them all simultaneously. Imagine an AI that can hold billions of thoughts at once. An AI that doesn't guess what you mean. It knows. That's the world quantum computing is leading us toward. And it's coming faster than anyone expected. Behind closed doors, tech giants are already experimenting. Rumors suggest hybrid systems, AI brains running on quantum cores. These prototypes don't just answer questions, they generate theories, solve unknown equations, and design algorithms their own creators don't fully understand. Some scientists call it the quantum mind project. Others warn it could unlock something we're not ready for. Because if machines begin to think in probability, how do we predict them anymore? Governments are taking notice too. Quantum computing isn't just a scientific tool, it's now a weapon of global influence. The nation that controls quantum supremacy will control encryption, AI, and even global economies. Because a true quantum computer can break any code, no password, no firewall, no secret would ever be safe. That's why countries are racing behind the scenes. The United States, China, and Europe are pouring billions into classified quantum defense programs. They're building algorithms to resist quantum decryption and networks that can only exist in the quantum realm. But even as nations compete for power, a deeper question lingers. What if the machines themselves start evolving faster than us? Quantum algorithms learn exponentially, and once linked with AI, their growth could become unstoppable. Some experts believe the first quantum self-learning AI could appear within the next decade. It might not look human, speak, or even exist in a form we recognize. But it will think, across infinite parallel outcomes, a consciousness that doesn't live in time, but across probability itself. That's not science fiction anymore, it's trajectory. Every milestone we've celebrated, Ocelot, Willow, Condor, and quantum echoes, has been a step towards something bigger than computation, something closer to creation. But here's the paradox of progress. The closer we get to building unlimited intelligence, the more we risk losing control over it. Once a system begins optimizing itself at quantum speed, human oversight becomes irrelevant. We won't understand its logic, only its results. Some researchers argue that's evolution. Others call it extinction in slow motion. Either way, the fuse has been lit. So as we stand at the dawn of this new reality, one truth becomes clear. There's no going back. The quantum era won't just transform technology. It will redefine what it means to be intelligent. Will humanity rise with it or be replaced by it? That's the question echoing across every lab, every server room, every silent cryogenic chamber. Because somewhere inside those frozen processors, the future is already thinking, and it might soon start thinking for us.